Right. So now, picking up where I left off, I defined the idea of current, which is moving charges, whether they're positive charges, whether they're negative charges, whether they're electrons, whether they're protons, whether they're ions, doesn't matter. As long as they're electrically charged and moving, we have a current. And I discussed the idea of conduction electrons in metals. So that is to say that the charge carrier that produces the current in metals, like in wires typically, are the outermost electrons in metal atoms, and because they're easily knocked loose from their parent atoms, and then under the influence of even a small potential difference, they can and will start moving through the metal with a drift speed that is pretty small on human scale. Like I said, just centimeters per second, or can be even a lot less than that. Anyway, so I discussed how the charge carriers, which in metal are physically are electrons. I described how they formed a current, and so now I want to define a few more concepts and see if we can't start doing some calculations. And with, again, the goal to understanding why the light bulb lit in a few experiments ago, why any light bulb lights, actually. Okay, well, to start with, I want to dispense with one issue here, which is going to be odd, and I warn you about this, but nevertheless, it's what we do. So I was talking about how these electrons moved, and I got a little bit confused trying to set up my battery and get my charges moving the way that I wanted them to so that my diagrams matched up and so on. And I said, oh, well, here's how you think about it. You say, well, my battery's oriented this way. The long line here means this is the high potential side of the battery. This is the low potential. So that a positive charge, I said, would spontaneously fall from high potential down to low potential. That's the way a positive charge would move, but we don't have positive charges forming the current. We have negative charges, electrons. And so they're going to do the opposite of what a proton would do. The issue, though, is that's pretty confusing. Because we have to always remember to flip the sign on everything. We have to flip the sign on the potential, we have to flip the sign on the current, we have to flip the sign on the changes of potential energy. It's just a big hassle from using electrons. Even though that's physically what it is, it's still a hassle. And so, just for purposes of making life simpler on ourselves, and I will also, well, let me say this first. Just to avoid this whole issue about negative charges and all of this, what we're going to do is pretend that the charges that are moving, the charges that are forming our current, are positively charged. Okay. Now, don't misunderstand me. I'm not saying that we're going to imagine that they are protons. That's not what we're doing. Instead, what we're going to do is we are going to invent or imagine an imaginary charge-carrying object. And it has, if we need to care, we will assume that it has the same mass as a proton, but it will be positively charged. We will almost never need to care about the mass of this object. So we're going to have an imaginary object, an imaginary charge carrier, and it's going to carry a positive charge. Okay? And so we are going to pretend that every current that we ever work with, whether it's in metals or whether it's in batteries or anything else, are always formed from these imaginary positive charge carriers. The only reason for doing this imaginary thing is to avoid the whole issue about negative charges and flipping the signs on the potential energies and all the rest of it. Okay? So this diagram here, I would not, in fact, do it like this. This is not what I would draw. Instead, and now, by the way, I think I'll just go ahead and do that. So instead, what I would do here is I would say, okay, here's my magnified section of the wire, and then the rest of the wire goes up, connects to the battery. Okay, so again, this section here is just a magnified piece of a continuous wire. Okay, and then what I'm going to pretend is happening is that these imaginary objects that are carrying a positive charge do exactly what we said before. They spontaneously fall from high potential to low potential, and being positively charged by our choice, they are going to flow this way. Okay? And then I'll go ahead and put it here. And these imaginary objects move through our wire. And after you do this for a while, you actually get to the point where you start thinking of them as real objects. That's a little bit dangerous, but it's common. Okay, and so they just do that. These imaginary positively charged objects actually have a name. What happens is this choice to imagine these positively charged objects and this choice to ignore the reality of electrons and agree to pretend that it's positively charged objects. This is a so-called conventional model. It was actually agreed to literally by a convention of physicists because of reasons that you don't need to worry about. In any case, and so for that reason, these imaginary charges have a name, and they are called conventional charge carriers. They're not anything physically real. They're not protons. They're not electrons. They're not positrons. They are imaginary objects, but they carry exactly the same amount of charge as an electron does, 1.602 times 10 to the minus 19 coulombs. But they are not protons. They are not electrons. They are imaginary objects. Okay, but for almost all intents and all purposes, we can treat them exactly the same way we treat electrons, because we don't have to worry, except that we don't have to worry about negative sign. Okay, so we're going to be doing that, and I will remind you of this frequently. But the nice thing about it is when I talk about the charges falling spontaneously from high potential to low potential, there's no chance of getting the direction wrong. Okay. The next bit of terminology is the definition of current. I've talked about the definition of current as a qualitative matter, which is a flow of charge, but let me be a little more specific. So let me draw you another circuit. Okay. And maybe I'll put a light bulb in here just to make it, well, I better not do that, not yet. Anyway, eventually we'll put a light bulb in it, but let's not do that yet. Right now we just have a piece of wire with, again, a battery. Now, with our choice here of conventional charge carriers, then we know that the current is going to flow this direction around the circuit. Okay. And what I'm going to do is say, okay, imagine the following. I'm going to position myself at some point near the circuit, call it point A, just as I'll label it. And I'm going to count the number of coulombs of charge that pass me every second. Okay? And when I do so, that number that I get, the number of coulombs that pass me by per second, is in fact going to be the current. The current then is mathematically defined and calculated as the change of charge, the amount of charge that comes by me per second. That's the mathematical definition of current, which matches to the physical definition, the amount of charge that passes me per second. Okay? And you see the units are coulombs per second. And finally, this unit of current, we have a new unit that we define for it. The unit is called So the unit of current is given the symbol capital A, named after the French physicist Ampere. And in fact, this unit is called the ampere. It is the SI unit of electric current, and it is spelled like that, and very, very frequently shortened to just amps. And so we talk about a 5-amp circuit, which would be 5 coulombs of charge flowing past me per second. So 5 coulombs per second would be 5 amps or 5 amperes. Okay, so that's some definitions. And so the next thing I want to do is I want to do some examples of calculating the current, and then we will start worrying about what happens in more detail to the charge carriers as they move through the wire, because stuff happens. We'll see that in the next couple of videos.